Hello all, welcome to the next session. So we are continuing the design of shear. Okay, we have seen so far what is shear, what are the different types of stresses available, and what are the different types of failure. And we are going to see now again the next real design of shear. Okay, so design of shear. So how to design for shear is, I hope you know the three stress names: nominal shear stress, that is tau b, shear resistance tau c max is the maximum shear stress any beam can take. Okay, so given most of the case to design for shear, I first you should know what is design for shear. Again, design for shear is nothing but what you are going to determine the only spacing. You are not going to put any stirrups dia or something. No, zero bend upwards, nothing you are going to design. You are going to design only the spacing between the stirrups. Okay, so to determine the spacing, what are the steps available? Okay, so given for any problems, mostly they will give you the shear force coming from outside, or they will give you the beam and load, and you have to calculate the SFD BMD diagram and then get the VU value. VU is the shear force coming from outside. B and D is the width and depth of the beam. FCK FY, FCK FY, I hope you know. Tau C and tau C max is, tau C is the shear resistance, tau C max they will give you. Step 1, you have to find the tau B value. Tau B is the nominal shear stress. I told you it is nothing but load by area. Load is the shear force which is coming from outside divided by the area. Area is the B into D of the beam. Okay, and I already told you, if this tau V is lesser than tau C max, it should be lesser than tau C max. I told you, right? If externally it should, whatever MPa is coming, it should be either 2 MPa, 3 MPa, 1.5 MPa, something like that. Else you should redesign, because your maximum capacity of your concrete to take the shear stress is, I have shown you in the previous table. I can show you again. This is the maximum shear stress it can take. Either if you are using M20 2.8 MPa, M25 3 MPa, something like that. So when your externally applied load is more than that, then you cannot even design. Obviously you cannot design. Consider a guy can take only 40 kg lift, you are giving him 100 kg, obviously he will die. So same story here, you cannot design if the external stress which is coming, the tau v is more than tau c max. You have to total redesign. What do you mean by redesign? You will increase the B and D. If you are increasing the B and D, tau v will come down, right? That's the story. Okay, if B and D is increasing, tau v will come down. If tau v is coming down, it will come lesser than tau c max, then you can design. Okay, so whenever you are designing a beam, so far we have seen designing of singly reinforced, doubly reinforced, everything. Similarly, you have determined B and D, AST, AC, everything, but in this, so you cannot finally say that designing for only for bending moment is a beam. Okay, even shear design will change the total design from start. If you are changing the B and D for shear, then the total beam design will change, right? You have to go back and design MU, AST, ASC, everything will change. So the step 1 is very important. Tau v equal to VU by BD, then it should be lesser than tau C max. Consider the step 1 is okay. So I am giving you some one externally coming shear stress is, consider it is 1.5 MPa, and tau C max is 3 MPa like M25. So it's over. Okay, it is lesser than tau C max. Then you are going to step 2. Then you are checking whether the 1.5 MPa which is coming from outside is lesser than or equal to 0.5 of tau C. Okay, what is tau C? What tau C is a function of PT, percentage of steel, and it is a function of FCK. Correct? I think I showed you in the table earlier. It is a function of, if you know the percentage of steel and if you know the concrete grade, you will know the tau C value. So consider I am giving you the value. This tau V which is coming from outside is very much less, like only 0.1 is coming, and without putting shear reinforcement at all, your beam can take that much of shear force. That is the tau C, right? I hope you know what is tau C. Tau C I have explained clearly in the previous. It is a capacity of your beam without shear reinforcement. So the externally coming stress is very lesser than 50% of your tau C. Then it is very safe in shear. No need to of any shear reinforcement at all. It is very few in number. But if it is greater than 0.5 tau C, and it is lesser than tau C, consider it is like the stress coming from outside is 0.7. Okay, so and your tau C is 1 MPa. Assume your tau C is 1 MPa and the externally coming load is 0.7. So it is in the range of 0.5 to 1, right? So although it is safe in shear, you don't need any extra shear reinforcement, but to avoid to have a satisfied economical design, not economical, it is for a safety factor, you should provide at least minimum shear reinforcement. Okay, but also only in the form of vertical stirrups. Understood? If tau V coming from outside is lesser than 0.5 tau C, no need of any stirrups. if coming if tau is greater than 0.5 tau c and lesser than tau c, so it is, although safe, we will provide the minimum shear reinforcement, okay, and also in the form of stirrups only. So what is the minimum shear reinforcement is, as per IS 456 they have given a formula, ASV by BSV, okay. B into SV, SV is the spacing between the stirrups. You can see the right side figure, I will tell you, but I don't have a clear picture anyhow. SV is the spacing between the two stirrups, okay. So B is the width, B is the width of the beam. So B into SV is nothing but a area, okay. In the B into, how many ASV is there? What is ASV? ASV is the area of the shear reinforcement. The formula I have given is N into pi by 4 d square. N is nothing but a number of legs, okay. So if it is two legged, I have shown you an example here, two legged means 2 into, three legged means 3 into. So how many legs are there in the B into SV area? B into SV, consider it is a plan. B into SV, you can take a paper and draw B into SV as a rectangle. In that, how many legs are there? That will be the shear that will be the percentage of shear reinforcement, okay, is equal to 0.4 divided by 0.87 Fy. That is the formula given. Multiplying 100 both sides will give you the minimum shear reinforcement, okay. And I hope you know what is ASV now. I have given you a formula here. You can pause it and you can note down the formulas. And they have given another requirement for this case. Your spacing when you are calculating the SV value, I hope I told you clearly 6 minutes before. Our purpose is to calculate that SV, okay, spacing between the shear reinforcement. After using this formula, you will get some spacing, right? SV you will get, because ASV is given. Two legged already you should know, and the diameter of the bar, it will be almost 8 mm only most of the case. So you know ASV, you know B, you know 0.4, you know 0.87 Fy. Substituting everything, you will get that SV value. That SV value should be lesser than or equal to 0.75 of D, or it should be lesser than or equal to 300 mm. Provide the minimum value, okay. So this is case 2, step 2. I hope it is clear. In the step 2, case 2. In step 2, case 1 was if tau v lesser than or equal to 0.5 tau c. Case 2 was tau v greater than 0.5 tau c and lesser than tau c. So for this is the requirement. You have to provide the minimum shear reinforcement. Last case, it's a very important case. If tau v, so the applied shear force coming from outside is greater than your tau c. Consider you can take only 10 kg. I am giving you 20 kg, okay. So it's like I can take only maximum 10 kg, but you are giving me 20 kg. So I will that extra 10 kg I will put some. I need some guide to ask, okay. So consider again I am repeating the example. Consider you can take only 10 kg, but I am going to give you in your hand 20 kg. So what will you do? You will ask some friend, right? You will ask some friend to come and pick the another 10 kg. Something like that. The friend can be in the form of inclined stirrups, vertical stirrups, or bent up bars. There are three people. Either you can provide inclined stirrups to take that extra shear force, or you can provide in a vertical stirrups, or you can provide in the form of bent up bars. There is a problem with bent up bars. You cannot provide the bent up bars only, okay, like a slab. You cannot provide only bent up bars. You have to provide stirrups also, because bent up bars is physically unstable. So if you are providing bent up bars, you are asking that guy. Consider one more time, I will repeat the example, sorry. So somebody is giving you 20 you can take only 10 kg. Somebody is giving you 20 kg, okay. So you took 10 kg and the remaining 10 kg you are asking some of your friend called bent up bars. That guy is coming in. So bent up bar, that guy is telling no, I can take only 5 kg. I need one more guy called vertical stirrups. He will call the vertical stirrups guy and he will give the 5 kg to him. So totally now you become a 3 people. As a beam you took 10 kg, 5 kg was taken by bent up bars, 5 kg was taken by the vertical stirrups, okay. So this is the 3 different ways of handling that extra shear force coming. Inclined stirrups, obviously most of the time it will be 45 degree or above, more than that, okay. So that is inclined stirrup. Vertical stirrup, I hope you know, it is single legged. Single legged is mostly we will use single legged stirrups nowadays in port and harbor structures and also in bridges. This 2-legged stirrups we will use in beam. 4-legged stirrups is if heavy width beam, and 6-legged stirrups if the width of the beam is 1 meter, 1.5 meter, something like that. Bent up bars, it's almost mostly we will not use. It will be used in the form of slab, okay. So this is the 3 form, okay. Now we will go into steps, real steps. So step 1 is nothing but VUS is equal to VU minus tau CBD. VU is nothing but a force, okay. So VU is the force coming. This, as I told you clearly, you understand the example. I told you I am giving you 20 kg. That 20 kg is VUS. I am giving you 20 kg. That 20 kg is that VU in the step 1, okay. So you told me that you can take only 10 kg. That is nothing but tau C into BD, stress into area. It is also a force. You told me you can take only 10 kg. That is, so what is the remaining kg we should design that stirrups and all? It is for 10 kg, right? That is nothing but VUS. Okay, extra shear force for which you have to design the reinforcement is VUS. VU is nothing but how much kg is coming from outside, that is from the SFT diagram. Okay, so for if you are using vertical stirrups, IS 456 has given a formula 0.87 FI ASV D by SV. If you are using inclined stirrups, this formula 0.87 FI AS, same formula, sin alpha plus cos alpha. For bent up bars you are using, I told you already, bent up bars cannot be designed for more than 50% of the extra force. So for 50% force you will use bent up bars, that formula 0.87 FI ASV. For remaining forces we will use stirrups, same formula above. Okay, for any case you have to, after designing this step 2, from step 2 what you will get is SV value, spacing between the stirrups. With the SV value you will go for the after finding step 2 you will do the check in the minimum of all down, that is step 3. Okay, you will check the given the answer should not be greater than the answer you are going to tell outside, that answer should not be greater than SV calculated from the minimum shear reinforcement. Okay, SV is very important, you should memorize this one. SV calculated from the minimum shear reinforcement. Minimum shear reinforcement I told you a little earlier, from this formula ASV by B into SV equal to 0.4 by 0.87 Fy, that one. And ASV should not be greater than 0.75 D. For inclined stirrups it is greater than a D, and spacing should never be greater than 300 mm. Like 300 mm is nothing but 30 centimeter long size scale. Okay, you have a long size scale, your one stirrup and second stirrup should not be more than that long size scale. Clear? So if you didn't understand anything for last 10 minutes, only this slide you should know. Step 1 you should know what is the extra shear force you should design for this all the stirrups and all. You should memorize this formula 0.87 FI ASV D by SV, these formulas. From this second step 2 you will know the SV value. Using step 3 you check whether your SV is correct. That's it. Okay, so we will solve some problems here. GATE 2008 question. They have given a beam of a rectangular cross section of width 230 mm, depth 400 mm, is subject to the maximum factor shear force. They have given 120 kN. FCK is M20 and main steel is Fe 4 and 5, but stirrup steel, I should tell you, stirrup steel mostly we will use mild steel bar because it is easy to bend. If you are using a tar steel, it is very already it is tar steel, it is already twisted. If you are further twisting for making it as a stirrup, there will be a crack developed at the corners. Okay, most of the case we will use mild steel for this. If it is a single legged stirrups, it is very easy. Single legged stirrups we can go for tar steel, but if it is four legged, two legged, four legged stirrups, and we will use mild steel. So stirrup steel is Fe 250, and they have given for the area of main steel provided the design the tau c is 0.48 Newton per mm square, and the beam is designed for limit state of collapse. Everything given, and they have mentioned spacing. What is the spacing? Spacing of 8 mm two legged stirrups to be provided is dash. And it is if you see the question very big, it is, then you should appreciate they have given so much of data. You see the given, they have given B equal to 230, D equal to 400, Fi 250, FCK 20, VU 120, tau c 0.48. So 2 legged stirrups of 8 mm diameter. So we know already that 4 steps. Step 1, find the tau v value because they have given VU, right? 120 factored, already factored force they have given 120 divided by BD, and it is coming 1.304, 1.3 MPa, which is greater than tau c. They have given tau c as 0.48, right? 0.48 is nothing but that much MPa you can take, but externally coming is 1.3. So the remaining force, right? Remaining force you should design the extra reinforcement. Okay, so this VU is equal to VU minus tau c BD. You just subtract the forces, then you have to design for this Newton. I think I have converted into Newton. So 0.75, I think something it will come, but it is a Newton 75840. So use the problem they have given is vertical stirrups. So V is equal to 0.87 Fy ASV D by SV. So SV is equal to, you substitute everything, you know Fy, you know ASV. ASV is 2 legged stirrups, 2 into pi by 4 8 square, and depth is given, and you know the shear force, extra shear force to be designed is equal to 115.32 mm, and you should do the step for checking. So what you should check for vertical stirrups, it should not be more than 0.75 D and it should not be more than 300 mm. So minimum of all the three will be your answer. Okay, so minimum of everything is, your answer is around 115.32 mm. That's it. Okay, so it's direct substitution. If you same step 1, step 2, step 3, just substitute, you will get the spacing. You can pause, you have any doubt you can ask me, or you can ask me to explain again. So next question, it's RRB 2012 question. In RC beam of width they have given 230, depth is 450, is subject to a factor shear force of 50 kilonewton. Okay, so force is 50, M20 concrete, maximum allowable shear stress, that is tau c max they have given is 2.8. For the shear reinforcement 8 mm dia 2-legged mild steel studs they have given, they are asking spacing. Same procedure, B is given, D is given, tau c max is given, VU is given, tau c is given 0.75 MPa. If they are not given, I think they didn't give you in a question, then you should approximately memorize this number. Okay, so step 1 tau v, VU by BD. Okay, so same procedure, step 1, step 2, step 3, exactly same procedure. Step 1 tau v equal to VU by BD. What is VU by BD? You are getting 0.48. It is lesser than tau c because tau c is 0.75, but it is greater than 0.5 tau c. Okay, it is lesser than 0.4, it is lesser than 0.75, sure, but it is greater than 0.5 tau c. So I hope you know, I hope you remember this. I told you some design. Step 2, it is coming under case 2. Tau v is greater than 0.5 tau c, but it is lesser than tau c. So we have to provide minimum shear reinforcement. So minimum shear reinforcement formula is ASV by B into SV equal to 0.4 divided by 0.87 Fi. So put 2 into pi by 4 h square, substitute everything, you will have the SV value 237.67 mm. So you should check for 0.75 D and 300 mm again because vertical steps and 237. Minimum of this 3 will be your answer. It is 237.67 mm. Okay. I hope you remember how this step 2 formula came. Step 2 formula came because of our tau v value. So you have step 1, you find the tau v value and put in which case it is following, whether it is lesser than 0.5 tau c or it is greater than 0.5 tau c or it is greater than tau c itself. So based on which case it is falling, based on that you have to use that formula. Okay. So we will go for one more problem. In a RC beam of width 230 mm, same question, they have increased from 50 kN to 100 kN. Exactly same question, the shear force is increasing. So if shear force is increasing, I hope you know it is tau v value is increasing. If tau v is increasing, it will be more than the tau c. So you see the same formula, the tau v now it is increased to 0.96. Okay, and it is greater than tau c. It is actually not 7c, it is tau c. So 0.96, it is greater than tau c. So what will you do now? We have to determine the extra shear force. What you should design that stirrups everything. So extra shear force is coming around 22. Okay. So you substitute everything here, bring the SV this side, you multiply everything pi by 4, 80 square everything, you will get a spacing of 439 mm. That's good, but I hope you remember 439 you cannot use, right? They are asking you for the extra reinforced spacing can be provided 439 mm. It's not allowed, right? As per IS 456, you see this first value, step 4, 439 you calculated now. 337.5 is nothing but 0.75 D. Okay, 0.75 into 450 will give you 337. 300 mm. I hope you know SV cannot be greater than 300 mm. This 237.67 is nothing but the spacing. I hope you know this case. You see the first case in the minimum of all down first case. Already we have calculated in the previous problem for the minimum shear reinforcement for the given case. Okay, minimum shear reinforcement, and you see minimum shear reinforcement is not a function of shear force at all. It is a function of B, ASV and Fy. So in this case it is 237. So the 237 is your answer. Okay, again I am explaining. First 439 is your answer you got. 337.5 is nothing but 0.75 D. 300 is nothing but your 300 mm given in IS 456. 237 is nothing but the spacing calculated based on minimum shear reinforcement. For the same question we calculated the previous problem, so I didn't include here. Minimum of all the three will be your answer. Okay. I hope all the 3 problems I have shown here exactly I repeated the same procedure. I calculated tau v value first, then I checked in which case it is falling, and then I verified. So if it is falling under which case, based on that I will calculate VUS, then I use that formula, then I find the spacing value, then I will check for all the spacing. Okay. So I will show last question, one more question. Now I am increasing the same question, I am increasing to 150 kilonewton. Furthermore, heavy shear force. Okay. So now tau v is 1.45, which is still greater than tau c value, and in the question, so they have increased the shear force to 150 kilonewton, and they have given a 1 point extra that for same shear reinforcement 8 mm dia 2-legged mild stirrups, everything is same, but they have given at supports there are 2 bars of 16 mm diameter, Fe4 and 5 are bent up. So there are 2 bars, they are of 16 mm diameter of Fe4 and 5 are bent up, they have bent, then the spacing of shear reinforcement will be dashed. Okay, they have given, so you have to design 2 things here. There is a bent up bar, so if there is a bent up bar, then you have to design bent up bar also and vertical stirrups also, because extra shear force will be coming, that extra shear force is divided for something for bent up bar, something for vertical stirrups. Okay, you see step 1, as usual I calculated tau v value, tau v is coming around 1.45, and then I am calculating VUS1. Okay, VUS1, step 2 I am calculating VUS1. VUS1 is nothing but a 0.87 Fi ASV into sin alpha. Okay, it is only a function of you see Fi is 415, ASV is nothing but 2 into pi by 4, 16 mm bar square they have bent, right? So that is just like a AST. Okay, 2 into pi by 4, 16 square into sin 45 degrees the bending, so 102 kilonewton. But we know the shear force taken by the bent up bars cannot be more than 0.5 of VUS, correct? Already we know what is VUS. For in our case it is 150 minus tau CBD is approximately 72 kilonewton. So total shear force coming itself, extra shear force to be designed is only 72 kilonewton. So the 0.50 percentage of that 72 is nothing but 36 kilonewton. So your bent up bar should be taking only 36 kilonewton. Okay, so VUS is equal to, now you know the VUS, you substitute that formula, you will have the SV value. Okay, so spacing of the so you are putting that 36 is taken by bent up bars. Okay, so remaining 36 you are designing the vertical stirrups. Okay, spacing of the, you see the question, they didn't ask you anything related to bent up bars. Okay, they are asking only for the, if already bent up bars is there, what should be the spacing provided for the vertical stirrups, then the value is very less, right? So I am using the bent up bars, vertical stirrups formula, VUS 0.87 Fi ASV d by SV. Putting all the values, you will get spacing 271 mm. So you see the step 6, 271 mm just we calculated with the shear force of 36 kilonewton, and 337.5 is nothing but 0.75 d, 300 mm is as usual IS 456 formula, and 237.67 is nothing but the minimum shear reinforcement which we calculated 2 problems before for the same beam. Okay, so minimum of everything is 237 mm, so you should provide the spacing, although if you are having a bed of bars you should provide a spacing of 237 mm. Okay, I think I have covered detailed shear force problems, okay, of all the formulas by changing different cases. So we will, I think also we have solved around 27 problems now. So if you have any doubt and you need more details about the shear related theory or problems, please mail me or ask for it. So we will have that in a separate session. So in next session we will see design for torsion and bond and development length, which is left in the beam design. Okay, thank you.